Over the past couple of years, cryptocurrencies have become extremely popular, and as a result, many people have been seeking to invest their money into them. Recently, there have been many talks throughout the news about mass adoption of big cryptocurrencies like Bitcoin. But mass adoption leads to higher chances of people using Bitcoin for scams, malware, Ponzi schemes, and other illegal activities. To prevent these illicit transactions from occurring, we must find a way to detect and classify them. And that is what our project is about. So we first started our project by applying various pre-processing methods onto our data. We made sure to include several classification models. We first implemented the k nearest neighbors, the decision tree, and then the gradient boosted decision trees. We compared them all amongst each other using the following metrics: recall, confusion matrix, and accuracy. Now let me tell you more about our dataset. It contains over 203,000 nodes, over 234,000 edges, and 167 features. The first feature is a transaction ID, which is a unique integer. The second feature consists of the time segments of all the transactions within 3 hours of the current transaction. Features 3 through 94 consist of local information regarding the current transaction. For example, the transaction fee. Features 95 through 167 are aggregated features that are obtained using the transaction information. Due to intellectual property issues, information about features 3 to 167 were not provided.
Next is pre-processing. We implemented correlation matrix, holdout, upsampling, and PCA. For the correlation matrix, we found the most highly correlated features and dropped them accordingly. For holdout, we did a 70-30% split. We implemented upsampling to try to balance out the label imbalance. For PCA, we tried to remove the unnecessary features. We created the tables and removed the highly correlated features and kept the ones that correlate with the label. Our correlation threshold was 0.95, and we were able to cut down the data down to 58 features out of 167. We implemented PCA but have been met with mixed results. We have implemented upsampling so that there's a one-to-one ratio between illicit and licit transactions. This improved the results for K9, but not to the same degree for the other classifiers. We tried upsampling by resampling the data with replacement, and we also tried a different upsampling technique called synthetic minority oversampling technique, or SMOTE, which attempts to create new data using existing data rather than simply duplicating existing data.
Results, we've done experiments to compare the performance of the classifiers. We looked at the accuracy and the recall, and we aim to provide these metrics using different pre-processing techniques. So for the decision tree, we performed grid search cross-validation to find the best parameters, which are entropy, max depth of 11, and minimum leaf sample of 10. Now the bar graphs you see here show the recall score and accuracy for each pre-processing method on these parameters. The core stands for features we handpicked from looking at the correlation matrix. PCA stands for PCA on the data, and the plus U sign stands for upsampling using the method of replacement method. As we can see here for the decision tree, it seems that the highest performance on recall and accuracy is on full data set, which does not have any pre-processing done to it except for the initial filtering of unknown labels. It gives us an 81% recall score, and we compare it with two different upsampling techniques in the bar graph to the right, and we notice no significant change between the SMOTE and plus U techniques, and plus U works slightly better. As for the KNN, we used k equals 5 and Euclidean distance. We did the same comparison as before. Here we notice that the pre-processing methods do change the results significantly. We notice that upsampling in all of cases increases the recall score, and we find that our PCA plus U yields the highest recall at 86%. But it is worth noting that we did not perform cross-validation on these results as it was time taxing, and we didn't have enough time. And for our next steps, we want to tune our parameters for K and N and perform cross-validation on our results for K and N. And we want to tune parameters for gradient descent boost decision trees, which we did not have enough time to tune, and compare the results across the models in our final report with existing work. And that is all for today. Thank you.